All right. Thanks for the introduction, Tarek, and thanks to the organizers for the invitation. It's a pleasure to be here in Providence, especially for such an exciting conference. I'll be talking about joint work with Balazem Strennerium and Ойку Юrttас. And the title says it's fast Nielsen-Thurston classification, so I'll remind you what the Nielsen-Thurston classification says. Here, we'll be studying the mapping class group of a surface, which is the group of homotopy classes of homeomorphisms of the surface. And the Nielsen-Thurston classification says there's three types of elements. Okay? There's the periodic, which means there's a representative homeomorphism that's finite order. There's reducible, which means there's a representative homeomorphism that fixes a curve or a multi-curve. And the third case is pseudo-Anosov, which is the most complicated, and I'm going to show you some pictures of what that means. Okay. So this is the definition of a pseudo-Anosov homeomorphism. There's two transverse singular measured foliations and a stretch factor lambda, so that the map stretches along one foliation by lambda and the other foliation by 1 over lambda. Okay, so I'm going to parse out all these words for you. This is a picture of a foliation. So everybody knows a foliation of R2. You can foliate R2 by parallel lines. So locally, a foliation of a surface should look like that. We know for Euler characteristic reasons you can't actually have a true foliation of a surface, and that's why there's singular points. There's one here and there's one here. Okay, so that's a singular foliation. It's measured, which means that you can measure, if you have an arc traveling transverse to the foliation, you can measure its length. Okay, and so you can measure the length of a simple closed curve, for example. Okay, the next word is transverse. If you have two transverse foliations, it'll look something like this. Okay, so transverse means what you think it means, and there's a picture. The last part is what stretches mean, and this is what it means for the pseudo-Anosov map to stretch in one direction and contract in another. If you take a little square that goes along the red and blue foliations, and you apply the map F, that's not great. It'll go to this long and skinny rectangle. Okay, it'll go to, instead of a square, it'll become long in one direction and skinny in the other direction. So that's what the pseudo-Anosov map is doing. You should imagine like a 2x2 matrix with eigenvalues lambda and 1 over lambda acting on R2. It looks like that locally. Okay, so that's a pseudo-Anosov homeomorphism, and so you should think of this Nielsen-Thurston classification as giving a normal form. Right? Every homeomorphism is either going to have a representative that's finite order, or a representative that fixes a submanifold, a one-dimensional submanifold, or a representative that has this very nice normal form. All right, we'll tighten these things. They were tight. Okay. Okay, so there's the obvious algorithmic problem. Somebody hands you a homeomorphism, let's say a product of Day and Twist, a product of generators. Figure out which type it is. Okay. Is it periodic, reducible, or finite order? Sorry, periodic, reducible, or pseudo-Anosov. And you want to do even more. The strong version is, if it's periodic, tell me what the order is. If it's reducible, find the reducing curves. Okay? And if it's pseudo-Anosov, find the foliations and the stretch factor. Okay? So that's the problem we want to work on. And this is our main theorem. There's a polynomial time solution to the Nielsen-Thurston classification problem. Okay? Last night I was in the lobby of the hotel minding my own business, and I was confronted by these two men with foreign accents, and they told me that they also could prove similar theorems. So Mark Bell and Richard Webb also have a polynomial algorithm to determine the Nielsen-Thurston type, which is the reducibility problem, and finding the reducing curves. Okay? So that's kind of news to me. Okay. So, oh yeah, right. We're not going to get into it in front of you guys. All right. There's some lots of prior work on this problem. I won't read the slide aloud, but there are exponential algorithms. A lot of work has been done just for braids. There's a lot of people who care about braids in particular. For braids, there's even a quadratic algorithm now. And recently, Mark Bell proved reducibility problem is in NP and co-NP. Okay, so those are some prior results, and some work in progress. Oh, I thought the screen was going to be lower. I was supposed to stand right in the middle here, but it's not working out. What's that? Yeah. not going to do it. What both of us are working on is to also solve the conjugacy and conjugacy search problem in polynomial time. You'll see from what I explained that it's not a big jump to go from what we're doing to that. So I won't really talk about this, but I'll give you some of the ideas. Okay, good. So those, that's Mark and Richard on the left, and Balazs and Oyku on the right. Okay, and lots of work has been done on the conjugacy problem. Hemion gave the first algorithm in 1979. There's no reasonable bound on the complexity. Mosier gave a solution that's at least exponential, but I'm not sure. Maser, Minsky, and Tao together give an exponential solution to the conjugacy and conjugacy search problem. And Mark Bell, again, proved that problem is in NP and co-NP. And there's tons of work on braid groups. There's a whole industry in braid groups with the conjugacy problem. If you've heard about summit sets or super summit sets or ultra summit sets, that's what that's about. Okay, so there's some work there. Okay, now I want to explain how Thurston thought about these problems when he was first proving the theorem. And so I'm going to do a little bit of history. These are notes that were taken during a class that Thurston was teaching. I think it's fall 1975. Does anybody want to guess who the student is who took the notes? No, it's not Stephen. It's Michael Handel. And so what Thurston, oh, by the way, these notes, I was going to mention, what was I doing at the time? I was just finishing up my second trimester, which was a big deal at the time. And so what Thurston's doing here is he wants to understand a pseudo-Anosov homeomorphism. The way he makes a homeomorphism is the surface here is a plane minus 4 points. And the way he makes a homeomorphism is he moves the points around. And if you think about the isotopy extension theorem or just think about intuition, that gives you a homeomorphism of the plane. Okay? And he wants to understand what it's doing. So what he does is he iterates the map on a curve. And over here, I think he's iterated the map 2 times, and you get this complicated curve. And so, so he's understanding this map by iterating on a curve. All right? So here's, it's I guess 40 years later now. Here's like kind of like an animated version. This is Thurston's example. Those 4 red dots are the 4 points moving around in the plane. If you like videos instead, this is actually Thurston's example as a taffy puller. A cross section of this is the Thurston example from those notes. And this video, I didn't take it, but it's from Trolley Square in Salt Lake City at the chocolate-covered wagon, which isn't there anymore. But anyway, it was good taffy. All right, so that's Thurston's example. We want to understand it, and as Thurston says in those notes, we want to understand it by iterating on a curve, okay? And so here it is. There's the homeomorphism. We're iterating on a curve, and you watch it go around. And now it's just done the homeomorphism a single time, and the curve is already getting pretty complicated, okay? So if you want to really understand this map, say understand what happens after 10 or 100 iterates, you obviously don't even want to draw the second picture in this sequence, so you need some new idea, okay? And Thurston's idea is we stare at this picture for a little while, and slowly you see something called a train track. Okay, that's a train track. That's Thurston's picture. And the usefulness of the train track, the first usefulness is you have this complicated curve, and you don't need the curve anymore. Because if I just put numbers on the train track, I can recover the curve. Right? If I can't reach, but if I put 5 strands going around here, 5 strands of curve going around here, and 2 strands going around here, and 5 strands going around here, you have no choice but to reconstruct the curve. Okay, so that train track encodes the curve. It's a nice compact notation for the curve. So we don't need the curve anymore. Let's just talk about train tracks. If I put weights, which I've labeled by x, y, and z, I should also mention, you should notice the switch conditions, right? What's the weight on this edge right here? It's 10, because you have 5 coming in from each side here, and those come together to give you 10. Okay, that's called the switch condition, but it's just intuitive. So we can not deal with curves, we can work with train tracks. So this is a train track, and if I put the weights 5, 2, and x equals 5, and y equals 2, and z equals 5, I get the curve I had before. And now I can try to understand the homeomorphism by applying the homeomorphism to the train track. So let's do that, and this is what happens. The train track gets more complicated, but the best possible thing happens, which is that the image train track has the same shape as what we had before. So we say the train track is invariant, okay? So we got the same shape again, but the weights are all changed. If you remember what letters corresponded to each color, you could figure this out, that over here, we now have x plus 2y plus 4z, etc. And so the upshot is you get a linear map. Okay, so we converted the topology problem of understanding this homeomorphism to a linear algebra problem. Okay, now I can understand the map by doing linear algebra. Okay, and what are the things you're going to do with this matrix? Well, you're going to find eigenvalues and eigenvectors. And this is supposed to relate, remember, to pseudo-Anosov maps, so there's supposed to be foliations and stretch factors. And so you shouldn't be too surprised that the eigenvalue is the stretch factor, and the eigenvector is the foliation. Maybe that's a little bit more surprising, but why does an eigenvector correspond to foliation? Remember, these three numbers are weights on the branches of the train track. Okay? And so if I take a train track and I have weights on it, then here's how I get a foliation. I replace each branch with a rectangle of that width. Okay? So this is width 1, that's width 2, and the other one's width 1 plus square root of 2. And since I did it that way, I can glue the rectangles together. The rectangles are already foliated, and so I get a subset of the surface that's nicely foliated. And if I collapse all the unfoliated regions to points, I've got a foliation on my surface, and that's the foliation. Okay? So in that example, even though there's only 3 points here, this actually is the foliation for that example. That example has a two-pronged singularity. So there you go. So you can really see, we can really find the foliations by hand. All right. Good. So, oh, and here's Thurston's train track converted to a foliation. Okay. Good. All right. So I'm going to explain, before I get to our algorithm, I'm going to explain probably what Thurston had in mind, a brute force algorithm that computes, that does Nielsen-Thurston classification problem. Okay? And to understand it, I mean, I'm not going to use Teichmüller space in this talk, but it's good to have this picture in mind. Okay? So this is the Teichmüller space is a space of hyperbolic metrics. So you fix the surface. Teichmüller space is a space of hyperbolic metrics up to isotopy. Okay? And I drew 2 points. The difference between these 2 points is that the one on the right has a very short curve. Okay? And at the boundary, okay, the Teichmüller space is an open ball. And Thurston proved you can compactify it by the space of projective measured foliations. Okay? So you take measured foliations and you say 2 are the same if the measures differ by a scale. Okay? And when you projectivize, you get a sphere, and you can topologize the union of Teichmüller space and projective measured foliations to get a closed ball. Why is that? What are these two things even have to do with each other? Well, both points in Teichmüller space on one hand and points in measured foliations on the other hand give you a function from curves to R. Right? Given a curve, you can take its length in the surface, if you have a surface with a metric. But given a foliation, you can take the length of a curve. Okay? So both of these objects are giving functions from curves to R, and that's why these two things have something to do with each other. Okay? Now notice I put these 2 points next to each other, and I won't really need this in the talk, but the idea here is as you shrink this curve, you're getting close to this foliation. Okay? What's special about that foliation is every non-singular leaf, they're all parallel to each other, and they're all parallel to that curve that's getting short over here. Okay? So one nice thing about this picture, one thing that's kind of going to be important in this talk is you have this space of foliations, okay? And you also have, sitting in there, you have simple closed curves, okay? So all the simple closed curves in the surface, you can do this construction. So all the curves in the surface are also sitting at infinity, sitting in the space PMF, projective measured foliations. And so if you know about the curve complex, which will come in later in the talk, you kind of have to think of both at the same time. You want to think of measured foliations, and you want to think of the curve complex as sitting inside. Okay? All right. The way Thurston proves the classification theorem is we've got this closed ball, and you prove the mapping class group acts nicely on it, and you just apply the Brouwer fixed point theorem. Okay? This is my favorite application of the Brouwer fixed point theorem. If there's a fixed point in the middle, okay, it turns out that means you have an isometry of your surface, so it's finite order. If you're fixing this point, then you're probably pseudo-Anosov. If you're fixing this point, then you're reducible, because if you fix this foliation, then you're fixing that curve. Okay? So the Nielsen-Thurston classification is just hunting for fixed points. Okay? And that's exactly what we're going to do and what I'm going to explain now. All right. Good. So this is already hinted at by my example, but what's nice about this setup is that you can compute, if you have a mapping class, you can compute the action on PMF. It's very explicit. Okay? It's a piecewise integral linear action, so there's integer matrices acting, but it's piecewise. And we already saw that in the Thurston example. We found a matrix, and it was acting on one piece of PMF, but we found an actual matrix. But the point is, if you have a mapping class, and I'll show you how to do it, you can literally compute the whole action on PMF and just look for fixed points. Okay? What are fixed points? Well, I have linear maps, so fixed points are just eigenvectors. Okay? Because everything's projective. I just got done teaching freshman linear algebra, and I just told them that eigenvectors are just fixed points in projective space. So anyway, that's what we're going to use. I didn't really do that. Okay. So all right. So so I want to write down this action. So I need an example to look at. This is the plane minus 3 points. Okay. In this case, PMF is a circle, which I've drawn as this square. And so we said that train tracks give you foliations. But what's even better is you can pick a finite set of train tracks that give you a cell decomposition of PMF. Okay, the cell decomposition here is 4 intervals. Okay, and so basically, because of the switch conditions, if I know 2 of these numbers, the number going around this loop and the number going around this loop, all the other branches are determined. Okay, and then I'm modding out by scalars, so it's really a one-dimensional space of foliations corresponding to each train track. And so that's an interval. And why do they intersect in a single point? Well, you can see that this smiley face curve, the smiley curve, is the only curve that can be drawn on both this train track and this train track. Okay, and similar with the other 4 points. So you can really see how this all fits together to give you a cell structure on PMF. Okay. All right, and what I want to do is I'm going to take a homeomorphism and actually show you what it does to this space. Okay. So here's the map. I don't know if you can see it, but I'm doing, I guess that's counterclockwise rotation of the first 2 points, so it's a half twist. Okay, I'm going to tell you what this does to PMF. Okay, so this is the train track that was on the first quadrant of my picture, and I'm going to apply the homeomorphism. I get this. So that was easy, but what's wrong with this? That's not one of my 4 train tracks, right? So I don't know where this is in my picture, right? I have to rearrange this picture so that it lies on one of those 4 charts. And so here's what I do. Well, first, I'm going to, I guess, anticipate here. There's going to be 2 cases. We're going to see the piecewise linearity. Okay? So what you're tempted to do is grab this train track right here by the neck and just pull it off. Okay? You just want to pull on it. And that makes sense. You can do that. Well, sorry, I didn't get there yet. That makes sense. You can do that because, remember, the way you should think of the train track is giving you this foliation with these rectangles that have thickness. So it makes sense. I can just rip off this top part. I can rip off that top part just like I'm ripping off a Band-Aid. Okay? And so we're just going to do it, and let's just watch what happens. I keep track of the weights because they're going to change. That x plus y, as I pull around, I'm just yanking it off. It was y plus x, now it's y minus x. And why did that happen? Well, this branch that I'm peeling off, right, that actually has weight 2x, right? Because x and x are coming together here to be 2x. So I had y plus x, I pulled off 2x, and now I have y minus x. And what's fantastic is this is one of my 4 train tracks, right? So I know exactly where that weighted train track went to in PMF. It's very explicit, and those are linear functions, obviously. So, what you're supposed to say, though, is, wait, that only worked if y was, weights have to be non-negative. So this only worked if y was bigger than x, or at least as big as x. Okay, and that's where the piecewise linearity comes from. I was only allowed to do that move if y was bigger than or equal to x. All right? So now you ask, well, what if y is smaller than x? What can you do? Well, let's look at that case. And, well, I can't pull off the x anymore because it's too big. It would rip off this whole thing here. But there's a symmetry between x and y here. I didn't draw it symmetrically, unfortunately, but there's a symmetry between the x and the y branches. So I'm just going to pull off the y branch now and just do the same thing. And that's what happens. The x plus y became x minus y. And great, again, I got one of my 4 train tracks, so I know exactly where this went in PMF. Okay? So in this case, for that to work, you needed x to be greater than or equal to y. Okay? So this is the picture. So you can see the piecewise linearity here. I applied a very simple mapping class to that train track. I bifurcated into two pieces, but both of them are linear. Okay? So that's the piecewise linearity. And in fact, I won't go through the other steps, but you can just now write down the whole map. Okay? The whole map is this blue region, which is the one we just studied on the last slide, got mapped to 2 different regions. Okay? And I gave you the formulas, okay, on the last slide. And the purple region just clicks over one. the green region clicks over one and gets shrunk by half, and the red region gets shrunk by half. Okay? So there's this fixed point here on the right, and all the other points are moving around, as you would expect if you've been around. So the points are moving around, but in a nice piecewise linear way. Okay? Yeah. So you can really see it. So actually, I'm almost done with the whole Nielsen-Thurston problem. Of course, I'm really studying SL2Z in this case, but I'm almost done because there's only one other generator for the mapping class group here, where you interchange the second and third mark points. And once I have that, if you give me any word, okay, I can just use these formulas and compute the action on PMF and find the fixed points. It's completely explicit. The problem is it's exponential, right? Because if I have a word of length 10, these bifurcations are going to pile up on each other. Okay, so that's where the exponential behavior comes from. All right. Good. Okay, so this is the brute force algorithm. So since you can literally compute this map, I don't know, there's not really much more to say. You just literally compute the map, and you just look for fixed points. And it's exponential. So the first step is maybe check if f is periodic. You have in a mapping class. That's easy because you can just find a few curves that fill up the surface. And there's a bound on the order of a period. If you fix the surface, the order of a mapping class can be at most some number that only depends on the surface. And so you can dispense with the periodic case quickly. The interesting part is pseudo-Anosov versus reducible. And so as I just said, you compute the action on PMF. That takes exponential time. And you find an eigenvector. If the eigenvalue is 1, that means you found a reducing curve. If your eigenvalue is bigger than 1, then you found a pseudo-Anosov foliation that's getting stretched. Okay, that's it. Okay, the complexity is exponential. The earliest known place where this is written is in the handwritten notes by Bleiler from the Castanem and Bleiler, that became the Castanem and Bleiler book. And there they say this method is due to Mosier, but I sort of suspect Thurston knew this. Hassam Hamidi Tehrani, who's pictured there, and Zonghee Chen were students of Joan Berman, and they gave a different version of this, which is also very useful to us. Both of them, I guess, went into finance. I don't have a picture of Chen, unfortunately. Okay. So that's the point of all this, is that it's very explicit. You can just write down the map. You've solved the Nielsen-Thurston problem if you're willing to wait exponential time. Okay. Okay. Now, here's our approach. How is our approach going to be different? Well, what you should think of, this isn't the best analogy, but the way you find eigenvectors, the way Google finds eigenvectors, is just by iteration, right? If you iterate your map on any vector, you get pretty close to the eigenvector. Okay? So, and so that's the basic idea of what we want to do. But the question is iteration fast or slow? Okay? So Thurston says every other point, besides there's source and sink dynamics, okay, for a pseudo-Anosov, and so the sink is going to stay where, the source is going to stay where it is. But every other point tends, he says, rather quickly towards the attracting point under iteration. This is in Thurston's famous research announcement on this work. Okay, and that sounds great. But then you have this theorem by Mark Bell and Saul Schleimer, okay, which says even with a fixed surface, you can find pseudo-Anosov mapping classes where the convergence rates are approaching 1. Okay, and for most surfaces, you can do it. The convergence rate can be exponentially getting closer to 1. Okay, so as they say, if Thurston was right here, then iteration would give an efficient algorithm. Unfortunately, it is not. Okay, that's what their theorem says. So that's an obstacle for us. We have to sort of resolve the difference between that and what Thurston's saying. Okay, so we'll see. Okay, let's see. Do I have time? Oh, yeah, I think I probably have time for this. So I'm going to explain also the other famous algorithm for finding pseudo-Anosov foliations. I couldn't find a technical word for the guess and refine algorithm. Like Newton's method is a guess and refine, but there's no word for this that I could find. Anyway, so the first key idea is something we've already seen in the Thurston example, is the idea of an invariant train track. So we already saw this in the Taffy-Puller example, that if you have a train track and you apply your map F, you have this nice behavior that sometimes F of the train track folds right back down to the original train track, and the weights have changed by a linear map. So what's nice about that is in that case, as in our Thurston example, you have a linear map, you have some cell in PMF that's getting sent to itself, and there's a fixed point. By the Brouwer fixed point theorem, there's a fixed point in the middle. Okay? Or, yeah, let's just say Brouwer fixed point theorem. Okay? So that's the goal of Vespina and Handel is find these invariant train tracks. Okay? And then you're good. Okay. So I think I already said, oh, I was going to mention this example is the one from my book with Benson, which is this big, apparently. I can't believe that exists, but if you've never seen a book. Okay, anyway, I don't know what, not sure what that was about, but I don't know what that was. Anyway, the thing I already said is that f maps this chart to itself. All right, and so that's a good thing. Now, what did Bespina and Handel do? Well, I mean, this is something you can just see from the picture. When you have one of these nice invariant train tracks, and you can apply f as many times as you want, you'll never see any backtracking, right? The f of any edge, f to the 100th of any edge, will just follow nicely along the train track. It's for the same reason that an actual physical train can't turn around on the train track, right? It's the same reason. Okay? So the idea of their algorithm is just start with any graph map and modify it until you get a graph map with no backtracking, and that's it. And then if you have that, that's actually the same as having a train track. Okay? So let's see. I think I'll show you just quickly. It's not so important for the talk, so maybe I have the pictures. I will show them to you. So here's that mapping class I showed you. I moved the points around so they're in an equilateral triangle. Okay? And you start with any graph. Okay? And the mapping class will give you it'll do something to that graph. And if you've taken algebraic topology, you know you can retract that back onto the graph. And you get a map of the graph to itself. Okay? The problem is there's going to be backtracking, right? You're not going to be so lucky. And if I apply this map twice, I already see backtracking right there. Capital C means going along C in the opposite direction, and little c means going in the forward direction. So you say, well, why did that happen? I can see why it happened. It's because of those pink guys in the middle. I have the end of A and the beginning of B go to the same place, well, all of B. Okay, so that's those two pink regions. And what's even worse is I see an AB in the image of the graph map. Okay, and if you think about that for a few minutes, you realize that's exactly what's causing the backtracking. And so what do? You just get rid of the problem. Okay, those two pink edges in the middle graph are going in the same place, so I'll just fold them together, and I got rid of the backtracking. And what they show is if you repeat this process enough times, all the backtracking goes away. In fact, in this example, we're already done. Okay, you can apply the map to this graph, and it's a finite check, which takes some thought, but it's a finite check that there will never be any backtracking on this example. And so that means you basically have the train track already. You have a graph map with no backtracking, you have a train track. And the map tells you how to make a train track out of this graph. In this example, it looks like this. But you just follow along the paths of the edges, and it tells you which way the trains want to go. Okay? So that's a quick maybe review for people who have seen it, the Bespina-Handel algorithm. But, oh, there's Mladen and Michael. But what I want to, it's an open problem to determine the complexity of the Bespina-Handel algorithm. It's at worst exponential. I expect it's exponential. But it's at worst exponential because the length of the words are growing exponentially, and so the number of times you can have that backtracking is exponential. Okay? And so you have to get rid of, oh, not again. Let's see. Oops. Oh, wait. Is it, okay, good. I don't know what's going on. Oh, wait. Oh, what's that? Wait. Oh, it's not showing up over here. I'm going to press enter. Did it do it? Oh, I have no idea how to get rid of that. Exit show. Is it still there? No. Slideshow, play from current slide. Oh, wait. Oh, it was on the screen? Oh, look at that. Oh, look. Oh, you're kidding me. You're kidding me. This is. Wait. Wait. Oh, okay. Wait. If I exit out and then hit that. Okay, I'm going to try it again. How do you know? Yeah, can you fix that? No, I can't. Look, watch. Check it out. Have you ever seen that? That's never happened. That's... Yeah, go back. Yeah, oh, yeah. Oh, wait, now everyone can see my desktop, too. I didn't clean it up. Is it gone? Oh, it's on 1. Oh, it's on 1. Well, it's all okay. Let's try 1. Let's go to desktop 1. Oh, there it is. Who saw that? Nice. Okay, slideshow, play from current slide. Yes, nice. All right, thanks very much. And yeah, Matt, thanks. Okay, so it's at worst exponential, and Mladen has told me that it's fast, for example, but the computer program doesn't work so fast. Okay, if you take Peter Brinkman's X-train program, which some of you might be familiar with, it runs the Best-Biene-Hendel algorithm. If you can give it a word of length 25, you're kind of out of luck. Okay, I want to do words of length 25,000. Okay, and this doesn't come close. Okay, there's a recent picture of Peter Brinkman. He was giving a talk on music synthesis at a conference on that stuff. Anyway, so but it's an open problem. I think it should be. I think there's exponential examples. You just have to find them. Okay. All right. Now this is the first very important thing for my talk today. The Agel cycle for what we've done. I'll call them Agel cycles. Okay. Here's the idea. Okay. Suppose you have a train track, and there's some choice of weights on the train track, so you get the pseudo-Anosov foliation. Okay. Suppose you have that, but it still could be that the train track is not invariant. It could be that when you apply f to the train track doesn't fold down onto itself like we saw in our examples. Okay. For example. Okay. What Agel does is he converts your not so great train track to a good train track. Okay. Train track that's invariant. All right. I'm going to show you how it works. Okay. You do these things called splittings. Actually, I already showed you splittings. Remember when I was peeling off those Band-Aids? That's an example of a splitting. So if you have a train track and it has a large branch, this branch is large because it looks like a split hair on both ends. And you can split it. Well, just rip off, yank this track where it says A and pull it up. You get the train track on the right. Okay. And that's exactly what we were doing when I was pulling off the Band-Aid before. And that's a picture from Ian's paper. I was in Cambridge yesterday visiting my nephew. We were doing scooters on the Charles River. And we came across this split bike path. Unfortunately, we weren't there to see the splitting itself, but it was still kind of nice. Okay. All right, so this is what Ian says to do. You have your train track. It carries, so for some choice of weights, it gives you the foliation you want, but it's not invariant. So what you do is you split all the branches of maximal weight all at the same time. Okay, there'll be maybe one, maybe more than one. And you just keep on doing it. Okay? And you can do it forever. Okay? And the first thing he says is that eventually, somewhere along the sequence, you're going to find the invariant train track you're looking for. Okay? He says way more than that, and I'll say the full thing on the next slide. But this is a way of finding an invariant train track, if you already have a train track that gives you the foliation. Okay? So here's the real thing he says. You have a pseudo-Anosov mapping class, and tau carries the attracting foliation. I mean, some choice of weights gives you the foliation for f. And you do this maximal splitting sequence. You split the largest branches at every stage. You keep on splitting. And then eventually, the pattern repeats. Okay? Eventually, you get to a train track, and you split some more times, and you get that train track again, except you've hit it with f, and you've decreased the weights. You've divided them all by lambda. Okay? The weights are always getting smaller because you're splitting the large train tracks. Okay? And moreover, that cycle, where it loops over again, that's a complete conjugacy invariant. Okay? So if you want to know how to get to the conjugacy problem from what I'm talking about, it's this. Okay? This is telling you exactly the main ingredient. Okay? I think this is better understood by an example. So this is, again, that example, the one from my book with Benson. And in the book, we find this invariant. It's not an invariant train track. We find this train track whose weights. This is just an eigenvector for us. So these weights on this train track give you the foliation for f. And I've drawn all the weights here. And there's only one large branch, which is the green one. That's the only one that splits at both ends. So that's the one I'm going to split, but I need to know all the other weights to know which way to split it. Okay? And 1 is the smallest weight in the picture. And so that tells you that's the one you can peel off. All right? So I'm going to do it. And there it is. And you can compute the weights on the new green branch, and it's smaller than what you had before. The weights go down when you do this. All right? Okay, and then I'm not going to write down all the weights, but you keep going. Okay? You split in the pink, split the blue, split the black, and you get this one. This is it. This is the special train track. We've entered the Agel. This is where it's going to start repeating. Okay? So I'm going to keep track of that graph over on the right. And I'm going to keep on splitting. Okay? So next, I'm going to split the orange and the red. They both have the same weight. And that gives me this graph. And then I'm going to have to split the blue and the green. You start seeing how doing this splitting is doing something like a homeomorphism, right? It's making all the edges more complicated. That's what you're supposed to get out of these pictures. Okay? This slide is important because it's, you do that splitting and get this picture. This slide is important because it's where I almost had a nervous breakdown making these pictures. And my student, Justin Lanier, made this picture for me. So actually, all these pictures are based on his sketches. We worked out this example with my other student, Shane Scott. They're both here at the conference. You should talk to them. They don't have any friends. Also, they're working on really interesting things. One of them's working on mapping class groups, and one of them's working on out-FN. I forget which one's which. But anyway, you should talk to them. But anyway, the point is, we did all this splitting. We had this graph on the top right, and we did all this splitting. And the claim is this complicated graph is the homeomorphic image, the image under F, of that train track. And it's hard to convince yourself looking at this picture, but I can convince you by just applying F inverse to this one in the middle. And if you apply F inverse, you at least see you have combinatorially the same graph. Oops. So, and you can check that the weights got decreased by a factor of lambda. All right. So that's the idea of the Agel cycle, is you start with a train track where the weights give you the foliation. You split, 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 and when you get to here, there's just a cycle. It just repeats. Okay, you don't actually get this graph again. You get f of that graph multiplied by 1 over lambda. So it repeats up to the action of f and scaling. Okay, so I'll call that loop at the end an Agel cycle. Okay, that's the conjugacy invariant for this mapping class. It's length 2. I was surprised to find that the length was only 2. So I'd love to see more examples of this worked out. Good. So there's some basic questions about Agel cycles. What possible lengths are there for Agel cycles? How does the length of this cycle relate to other invariants? I think nothing is known, basically. Or maybe Ian told somebody, maybe Balazs, that it can't be length 1. Maybe because you have a hyperbolic manifold with 3 manifold with 1 tetrahedron. Okay, back to the iteration scheme. Okay, and I'll explain how the Agel cycles come in. So we have this iterative scheme, and this is the algorithm. Okay, this is our algorithm. Okay, first you have to do some setup. You fix which surface you're talking about, and you fix any curve, but you fix it once and for all. Okay, we're going to iterate on that curve. Okay, and E of n is some quadratic function. That n is what you should imagine being the word length. So you just fix some function of n. Okay? So there is such a function, and we know what it is. The input is a product of n Dane twist generators. So you input your favorite product of Dane twists, so word of length n. And the algorithm, again, you check for finite order. Again, that's the easy case because you know there's a bound on what the finite order can be. If it's not finite order, you just compute. You figured out, you picked n up here. You have this function here, so E of n is just some number. You compute f to that power of the curve. So you iterate on the curve like Thurston did that many times. All right? And the point is, at that point, you're in the linear piece. Okay? You may not be close, you may or may not be close to the eigenvector, but you're in the same linear piece. So if you compute the matrix that's acting on this iterate, it's the same as the matrix acting on the fixed point. Okay, so there's some big linear piece in PMF, and you're in that linear piece. And you may or may not be actually close to the eigenvector. Okay? So since this curve, f to the e of c, is in the right linear piece, the eigenvectors of the matrix acting on that point are the foliation or the reducing curves. So you don't have to compute exponentially many matrices. After you figure out this iterative C, you just have to compute one matrix because you know which matrix to look for. Okay? That's the idea. All right, I'll make a couple of comments. So the upshot, what you should read, this is a long slide, what you should read from this is there's some power, okay, which depends on n and depends on the surface. And then if you take this small power of the standard curve, you're in the right linear piece. You don't have to understand all the linear pieces, just this one. Okay? This number E of n is known. It's not known to me at this moment. I think if I got the right people in this room together, Tariq and Richard and Mark, we could figure out this number, this function. Okay. You need a value for the linear conjugacy bound of Mazur-Minsky, which I think you guys know. Yeah. Okay. Maybe the more surprising thing is that this function E should be able to be replaced by a constant function. Okay. So if you tell me you're on a surface of genus 3, then the 10th iterate should always work, okay, independent of word length. And I'll say more about that towards the end of the talk. Okay, so I'm going to explain why this algorithm works, why when you apply your mapping class to a curve, within some small number of iterations, you get to the right linear piece. Okay. Here is the first ingredient. Okay. Pre-periodic length is the theorem of Mark Bell. Remember in the Ian Agel picture, you had a graph and a train track. You split, 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 and then you get into the cycle. Okay? The question is, how long do you have to split before you get to the cycle? Okay? And Mark Bell tells us. Okay? He says the number of splittings needed to arrive at the Agel cycle, okay, starting from a standard train track, is bounded above by a quadratic function of word length. So you fix some standard collection of train tracks, like in my picture of PMF for the plane with 3 punctures. Okay? So you fix some standard train tracks, and then you have some word, and the number of splittings you need is a quadratic function of the word length. Okay? And the key for this is, again, this linear conjugacy bound of Mazur-Minsky, which says if you have 2 elements of the mapping class group and they're conjugate, and you know their word lengths, then the element that conjugates from one to the other has word length that's bounded by the word lengths of the 2 mapping classes that are conjugate. Okay? The idea, well, maybe I won't say. Okay. So that's the first thing. That's the first ingredient. You can take that as a black box. The second ingredient is the nesting lemma. You shouldn't really read this slide if you've never seen the nesting lemma before. I sort of felt obligated to say the pieces. The corollary is maybe the most important thing. And I'll show you a picture of this in a minute. The corollary is that if you have one of our invariant train tracks, like the ones I showed you, then if you apply some power, m here only depends on the surface, okay? Then f to the m, oh, sorry, let me read the first line of the slide before I explain this. So this is that thing I was saying earlier in the talk, that you have PMF, okay, the space of foliations, but you also have simple closed curves sitting there, right? Because the simple closed curves gives you a foliation by thickening it up to a foliation, okay? And so train tracks give you charts on PMF, but they also give you a subset of the curve complex. Okay, you just look at all the curves that are carried by that train track. Okay, you get by integer weights on the train track, and it turns out that subset of the curve complex is a half space. Okay, meaning it's some infinite diameter quasi-convex subset. Okay, and the complement is quasi-convex. Okay, so that's kind of this interplay between foliations on one hand and curves on the other hand is. It's very beautiful, and it's what drives a lot of this. So the corollary is that if you take that half space, and this is an invariant train track, and you apply f to the m only depends on the surface, then not only are you contained inside here, but the one neighborhood is contained inside. Okay? I'm going to show you a picture. This is probably a lot to absorb if you haven't seen it before. Oh, I also wanted to throw Chris's picture up here. There's a nice proof of the nesting lemma that's in a paper by Gadre and Tsai. Well, you're shaking your head, but it's there. Oh, sorry, is that, like, okay, sorry. I'm sorry. All right. I understand. Okay, got it. We understand each other. I'm sorry for that. Okay, so here's the picture for the nesting lemma. Here's the complex of curves. The vertices are simple closed curves on the surface. The edges are for disjointness. It's a hyperbolic space, so I'm just drawing it as a disk. You should think of the hyperbolic plane. And we said a train track gives you a subset of the curve complex. Okay, it's a half space. Okay, and what the nesting lemma is saying is that if you apply some power of your mapping class, you get some other half space, and it's contained inside. Okay, and again, m here only depends on the surface. And if you do it again, you go further inside. And again, the point is there's some definite distance here. Okay, there's distance at least 1. So this is actually a proof that the curve complex has infinite diameter because we're making progress. Okay. All right. So that's the nesting lemma. So if you like, this is the picture. All right. Ingredient 3. There's only 3 ingredients, and then I just put them all together and I get the algorithm. Okay. So there was Bell's bound on the length of the pre-periodic length. There was the nesting lemma, and there's this. Okay? So if I have a train track, there's some special curves. The train track gives me a chart on PMF, and the vertices of that chart are curves, and those are sort of special curves. Okay? And those are called vertex cycles. So we saw that in our example of the plane with 3 mark points. Right? There was 4 vertex points. Okay? Those are the vertex cycles. Okay? The observation is that if you have 2 train tracks and they differ by 1 splitting, then the vertex cycles are within some distance that only depends on s. Okay? So in other words, the upshot is if you do a single splitting on a train track, you're not moving very far. Right? A train track gives you this subset of the curve complex, this half space. If you do 1 splitting, you can't be jumping very far. Okay? Those are the 3 ingredients, and you just put them together and you get the algorithm. But remember, the point of the algorithm was to say that if you start with a standard curve and you iterate some bounded number of times that only depends on the surface, then you get into the right linear piece. Okay? So the linear piece we're aiming for is this angle piece. Okay? We said that there's this, you're trying to get into the piece corresponding to an invariant train track. Okay, so first you say Mark Bell. So what's the, maybe I'm missing some words at the beginning, I should say. So you fix once and for all a cell decomposition of PMF, just like in my example, okay, with the plane with 3 mark points. And you pick your curve C so that it's a vertex cycle of one of those train tracks. Okay? So we know the fixed point for the pseudo-Anosov is in one of the standard charts. And so I want to know how many times do I have to split the standard chart to get to Ian-Eagle's cycle, okay, Ian-Eagle's region. Okay? And so, well, that's basically what Mark tells us, Mark Bell. Says by ingredient 1, there's a quadratic bound on the number of splittings you need to go from your big standard chart down to Ian-Eagle's chart. Okay? It's a quadratic bound in the word length. Okay? Now, that gives us a bound on the number of splittings. Ingredient 3 says if you did this many splittings, you haven't gone too far in the curve complex. Okay? So that's ingredient 3. So we now have a bound on how far we've moved in the curve complex doing these splittings. Okay? And by the nesting lemma, we know every time we apply the nth power of our mapping class, we're moving distance, at least distance 1 in the curve complex. Okay? So the first 2 parts tell you how far you have to travel to get to Ian's region. And the nesting lemma says, well, if you take this power of your mapping class, you're going to be making progress towards the goal. Okay? And so you get to the linear piece. All right. That's it. That's the proof of the algorithm. Okay? Let's see. I want to say, maybe I'll show you a few pictures of what happens in the reducible case. I don't think anybody was keeping track of time while we had that interlude. And so I can go as long as I want, I guess, and it'll be fair. Okay. All right, that wasn't planned. All right, the reducible case, this is the issue. There's 2 issues. Issue number 1 is that a reducible element doesn't have an invariant neighborhood. Let's look at the example that we already had, right? Remember, all the points in this circle are getting rotated around this way. So points on this blue edge are getting repelled from this fixed point, which is that vertex, and points on the red edge are getting pulled in. Right? So if I draw a little neighborhood of that vertex on the right, it's not going to get taken inside itself, because that's an issue. Okay? The way you deal with it is you just think about half neighborhoods. Okay? So in this case, the important neighborhood is a little half interval on the red piece here. That's a piece that gets taken in itself, and that'll be a matrix with eigenvalue 1, and you'll see the reducing curve. Okay? Issue number 2 is, right, remember in the pseudo-Anosov case, you start with a standard train track and split some number of times to get to Ian-Eagle's train track. Okay? Well, that would be great if your pseudo-Anosov looked like this, right? You would just split the standard train track and you just do Ian's process on both sides. Okay? But the typical reducible picture is that the pieces are mushed together. Okay? And so before you get to do the Ian-Eagle splittings, you have to split apart the orange pseudo-Anosov piece from the purple pseudo-Anosov piece. So we call this an alley right here in between the, so in the standard train track, these edges are smushed together. They're actually the same edge. And so you have to somehow disambiguate the 2 pseudo-Anosov pieces. Okay? And the lengths of these alleys, there's an alley here of length 1, 2. The length of that alley goes exponentially. So that's an issue. And it's resolved by building off Jing Tao's thesis and using some work of Maser, Mosher, Slimer. This is the most technical part of our work, And I'm not going to say too much about it right now or anything else. Okay, so here's the proof is here. And these are experiments done with, well, like I said, it's great to have the existence of an algorithm, but I want it to work. I want to do experiments. And Toby Hall, who's Oyku's advisor, wrote a computer program that does, well, it just iterates on PMF. It just computes the action of a mapping class on a curve. And as I was saying, we want to do long words, okay? And if you see this, we're doing words of length 14,000 in a little over 2 seconds. Okay, you can go up to 25,000 as long as you want. Okay, it's just multiplying matrices. It's very fast. Okay, again, even to go up to a half a second, you already have to go up to length 6,000. So you can do this very fast, and this is where we got the idea that this function that you have to raise the mapping class to is actually constant. So it's always some small power, and you're already in the linear region. Okay, so maybe I'll end by going back to these examples by Bell and Schleimer. So these are some of the examples that Bell and Schleimer considered. Okay, these as k increases, the convergence to the fixed point is very slow. Okay, so you might want to ask, well, how does our algorithm work on those examples? Okay, and using that program, you can verify the convergence is slow. You get 1 decimal point at a time, or whatever, something like that. You can check. But here's the amazing thing: you can take k to be 10,000, or any number between 0 and 10,000, and the number of iterations you need to get to the right region is 2. Okay, independently of k. So no matter how big it is, so it's somehow, it doesn't matter that you're getting to the point slowly. What's more important, what happens is the linear piece is very big. So I don't care how quickly you're getting to the fixed point. As long as you're in the linear region, you're where you need to be. Okay, so as is often the case, Thurston has the last laugh. An iteration does work quickly. So thanks very much. Yeah, Sam.
I have a question about the order thing. So
yeah.
When you use Hegel's theorem about the existence of a periodic invariant
Yeah.
split,
Yeah.
in his paper, he assumes you have an invariant trap for pseudo-Anosov.
That's right. That's right. That's right. Again, the idea is you cover PMF by finite linear charts, just like in my square example. Okay, you know the pseudo-Anosov fixed point is somewhere in one of them. You don't know which one. Okay. But Ian then says, you don't know which one at this point, but Ian then says there's finitely many splittings to get to his chart. But that means you only have to move so far in the curve complex. But all the different vertices of all the different charts are some finite ball in the curve complex. Right? So in the end, we're using distance in the curve complex. So even though there's this huge number of charts, and you don't know which one the pseudo-Anosov piece is in, you're not moving it all in the curve complex when you pass to a different chart. That's the point. So the point is that, oh, I see, I explained what works in the pseudo. So the point is that in both cases, so what you do in the pseudo-Anosov case and the reducible case is you find some number, okay, and you raise your mapping class to that number, apply it to the curve, you're in one of these invariant neighborhoods or half neighborhoods, okay? And there you're either going to find an eigenvector with eigenvalue 1, so you're doing both at the same time. I explain them in different segments of the talk, but the point is there's some power, you apply f to that power on your curve, you're in a good region where you can see the eigenvectors. That's the point. Yeah.
A couple slides back, when you had the graph of the runtime, it seemed like there's a lot of clustering around the curve and some outliers above it.
Yeah, I don't know if we did enough examples, but yeah. The good news is we're talking 3 seconds here as opposed to all day. And yeah, maybe one good, I mean, again, what I care about is running experiments. For example, a question that's not known is what's the smallest dilatation or stretch factor on a surface of genus G? Even for genus 3, that's not known. But now, if you can get it down to the lowest million examples, you can find the answer tomorrow. Yeah, yeah.
So when you run the algorithm, you say you don't actually know what the number is. You just plug it.
No, we know what the number is if Tarek tells me his theorem with, who is it? With Sam. Oh, your theorem. Okay, sorry. But I like Tarek better, so I'm going to ask him. Yeah. Yes. For the example. Oh, I see. Yeah, that's right. So this is people in other fields. An algorithm is good even if you can't prove that it works. And the way that we were doing that is You just iterate on the curve some number of times, and then you see the matrix stays the same 10 times in a row, and you know you're in the right piece. So you're right that those experiments are sort of, yeah. So it's not, yeah. So that graph should be taken with a grain of salt. That's what I want to say. Yes. Yeah, Mark.
Sorry, so if you say you're stopping after you've done calculations and you stay in the same piece for 10 steps, doesn't that mean that, like, in these examples, you could potentially be very, very slowly crossing over this cell which doesn't contain?
Yeah, that's right. That's possible, but no, it's not that simple-minded in that it stops as soon as it sees the same matrix twice. So actually, Oyku knows the inner workings of the program, but I trust that she went far enough that she knows it's in the right. Yeah, and you can check. You can verify. Yes, that's right. Exactly. That's right. That's the point. Yep. Exactly. Yep.
That was a really nice talk.
Thanks.
So it's conjectured that like, the stable nominations of pseudo-Anosovs are typically generic.
Typically generic. What does that mean?
Oh, so like the prongs, like...
Oh, yeah. Sorry.
All the complementary regions of the nomination.
Yeah, that's right.
Ideal triangle.
Yeah, that's right.
Right. So, Agel's cycle of train tracks, when the nomination is not generic, does not have maximal train tracks.
That's right.
So, the space of carried curves is not a half space in the curve complex.
That's right.
It's codimension 1.
That's right. That's right. You have, yeah.
So how do you overcome those?
There's no issue. I mean, yeah, we can talk about it, but yeah, there's no issue. Yeah, it just works. Yeah.
There are no other questions? Let's thank Dan again.